So here we have a section basically without numbers. So that's kind of a nice change. Qualitative chemical analysis. Refresher on what qualitative means. Qualitative, it has to do with the quality of something. Finding out the kind of ions present. What's in the solution? Quantitative has to do with quantity. Quantitative analysis, which is what I enjoy, is concerned with finding how much, finding the quantity. But here we're talking about qualitative analysis. And qualitative analysis by selective precipitation is a very important historical technique. That's what we tend to refer to as wet chemistry. This has largely been replaced by modern instrumentation. So there are a lot of these things where you can find out what ions are present without mixing solutions and precipitating and doing things like that. You put your sample in a sample tube and you stick it in a machine and you push the button. And it says sodium's present, calcium is present, lithium's present, done. Of course, the machine costs like $50 gazillion, but so this selective precipitation, we did an experiment last fall where it was a problem because there was some chloride ion in the distilled water, the deionized water had chloride, right? Well, how could you, without using an expensive instrument, find out if there's chloride in your water? Add some silver nitrate. Silver nitrate precipitates chloride. If it gets cloudy, bang, you've got your answer. There's chloride in there. That's qualitative analysis. It's there or it's not there. We don't care how much. So this sort of a process, you take a sample that has a mixture of metal cations and you add several precipitating agents in sequence. So you add one agent. So here you've got your original mixture, 3 different cations. You add a precipitating agent, one of them precipitates. So you're going to separate it out. You could decant it, you could filter it. There's lots of different ways to separate the liquid and the solid. Now you have a solution containing, what's left, B and C. You add another precipitating agent. You get another precipitate. Decant the liquid, pour the liquid off the top, and now you've got A over here. Yes?
In reality, you'll never get rid of all of those things.
You won't get rid of all of them, but you can get down to a level where you don't care. Like 10 to the minus 8 molar, where it doesn't matter.
Okay.
Yeah.
It doesn't matter.
So group 1, it seems like there's something missing here. Whatever. This is a typical, we call this a qual scheme sometimes. This is a typical sequence of adding things. So first you're going to get rid of group 1. These are the insoluble chlorides. So you take your mixture, you treat it with 6 molar HCl. Most chlorides are soluble except silver, lead, and mercury 1. They form insoluble chlorides. And so you're going to see a precipitate if 1 or more of those are there. Now, if they're all 3 there, your precipitate is going to contain all 3 of them. And so then you might have to do some other things to figure out which of them are in there. But the book doesn't talk about that, so I'm not going to talk about it. So you would precipitate out the silver, lead, and mercury 1 and separate the solid from the liquid. Then you'd take care of group 2. These are acid-insoluble sulfides. So that mixture that you have left now is acidic because you put 6 molar HCl in it. So now you're going to add hydrosulfuric acid. That is a weak diprotic acid. So H2S ionizes into hydrogen ion and hydrogen sulfide ion. The hydrogen sulfide ion ionizes into hydrogen and sulfide. So the concentration of sulfide, which is what's precipitating the cations, is going to be pH dependent. Is this going to be higher or lower at high pH?
Higher.
If the pH is high, there's very little hydrogen ion. And so the sulfide ion concentration will be larger. The situation we have is low pH, which is high hydrogen ion concentration. So this is an equilibrium. If there's lots of H plus around, it causes the reverse reaction, and you're going to have a lower S2 minus concentration. Okay? So at low pH, acidic conditions, your sulfide ion concentration is low, and only the most insoluble metal sulfides will precipitate. That's these guys. Mercury 2, cadmium 2, bismuth 3, copper 2, tin 4, arsenic 3, lead 2, and antimony 3. And just for visual interest, there's a picture of some of those guys precipitating. Now, you could probably tell if you have lead because he forms a precipitate that's a very different color.
Can you start with something in particular? Or is this
We're-
just a general piece?
It's a general scheme.
Okay.
And you would tend to add these reagents in the same order every time, because if you did it in different orders, it might not work. There's some things you need to get rid of, some of the things, because they'll react with almost everything.
Got it. So this is just an order of how to.
This is an order that you would treat your solution in, and what you could expect to precipitate out at each step. After that, you would go for group 3, the base-insoluble sulfides and the hydroxide. So we're going to add more base, probably sodium hydroxide, and you're going to add more hydrosulfuric acid. Well, because maybe you used up a bunch of it when you precipitated the other stuff out. You want to make sure there's enough there. So the added base is going to shift that H2S equilibrium. That should be singular. Well, I guess there's 2 of them. Never mind. Squirrel. That'll increase the sulfide concentration. So there are other metal sulfides that are just more soluble than that group we just looked at. And so if we have a higher sulfide concentration, they will precipitate. And that's these guys: iron 2, cobalt 2, zinc, manganese 2, and nickel. Well, this is also now a basic solution. It's got hydroxide ions. And so we'll see that chromium 3, iron 3, and aluminum 3 will precipitate as hydroxides. So you'll get these guys coming out. And again, you remove the solids. In group 4, all you've got left are alkali and alkaline earth metal ions, group 1 and group 2 ions. So the alkaline earth metals, group 2, can be removed by adding ammonium phosphate, because these will be insoluble with the phosphate: magnesium, calcium, and barium. So you'll get phosphates precipitating out. The thing about those darn alkali metals, group 1, they don't precipitate with anything. So now the only thing that's going to be left in there are sodium, lithium, and ammonium ions. I'm not sure why they left potassium out. You know, I think I probably left potassium out. Or maybe it was supposed to be potassium instead of lithium.
Yeah.
It's supposed to be potassium. There could be lithium in there too, right? There could be. So at this point, you're going to identify what's present with a flame test. Sodium is really easy to spot. It gives this really bright orange, yellow flame. Potassium is very pretty, but it's not as easy to see. It gives this lavender flame. And lithium also gives a color for a flame test. I just can't remember what it is. It might be green. I don't remember. Don't quote me on that.
Is lithium supposed to be there?
I don't think lithium is in the book, but if you had lithium ion in your solution, it would be there still. all the alkali metals. So I'm not sure why they left lithium out. So here's your big scheme. I think it's maybe because they didn't have lithium in here. But if you started out with these guys, when you add this, these guys come out. When you add this, these guys come out, basically. So there's your big qual scheme.